Okay, so we're back again, and we're on our last part for this week. And so, what I'd like to do now is talk about the properties of invertibility. And so, what I'll do is I'm going to write it down a bunch of conditions which are equivalent to a matrix being invertible. But the way we should sort of think about this is through the process that we discussed the last time. So let me run through that very quickly for you. So A is an m by n matrix. And let's say A is invertible. So A inverse exists. And if A is invertible, then what we're going to be able to do is we're going to be able to start with A here and put the identity on this side and then transform this into the identity on the left and A inverse on the right. Okay. And this uses the Gaussian elimination procedure. But the thing one should notice is that if we do apply this procedure, what we need is we need the identity matrix on the left. So let me write out the identity more clearly here. So what does the identity matrix look like? It has ones all the way down the diagonal. So what that means is that you have to have n pivots. I mean, if you don't have n pivots, then the game is over. You can't do this procedure. So you have to have n pivots here. And so A is invertible. So one thing we could say is A is invertible if and only if A has n pivots. Okay. And we've seen other consequences when you actually have n pivots. So for example, if you have n pivots, then AX equals 0 has only the trivial solution. AX equals B has a unique solution. And so this forces really strong conditions on systems of equations, linear independence, and spanning. All right, so let me state the theorem. And so here's a big theorem. So let A be an m by n matrix. Okay, so the following statements are equivalent. All right, so we've actually seen the equivalence of the first two statements. So the first statement is A is invertible. Okay, and that's the same thing as A has n pivots. Okay, so if A has n pivots, then AX equals 0 has only the trivial solution, X equals 0. Okay. So what does that mean? Well, it means that for the columns of A, are linearly independent. Okay, so remember if you take the columns of A to show linear independence, what you do is you look at AX equals 0 and you show that it only has the trivial solution. We actually went over this a while back. Okay. So what does the linear independence of the columns mean? Well, it also means that when you take the linear transformation from Rn to Rn, this is 1 to 1. Okay, so you can translate that into linear transformation language. Okay, now, now the next thing we also know is we also know that we can apply this to systems of equations. So AX equals B has a unique solution. Okay, so we saw that in several different guises, and one way to say is that the columns of A actually span Rn. Okay, so that's another consequence. So the columns of A span Rn. Okay, so this is kind of the meta theorem which connects all these ideas together. And then finally, we could again discuss things in terms of linear transformations. So when you think of A as a linear transformation from Rn into Rn, this is onto. Okay, so all 8 statements here are equivalent to one another. So if you know the linear transformation, for example, is 1 to 1, you know that A had to be invertible, and vice versa. Okay, so you have one, you have them all. Okay. So let's do an example where we actually apply these equivalences to actually determine whether A is invertible. So determine if A equals the matrix 1, 4, 2, 2, 7, 3, and 1, 7, 5 has an inverse. Okay, so there are many ways to skin a cat here. Okay, there are 8 different ways. So I can actually try to find an inverse for this thing, but I want to be a little bit lazier. So why don't I just look at the homogeneous system and see whether it has the trivial solution or not? Okay, so let's try that. So consider AX equals 0. Okay, so let's just do this. And we actually know how to do this fairly quickly. 1, 4, 2, 2, 7, 3, 1, 7, and a 5. And 0, 0, 0 here. Okay, so we can do that. So again, let's use Gaussian elimination. So keep the first thing the same, 1, 4, 2, 0. And then what do we get? We get a 0, minus 1, and we get a minus 1 here, and a 0. Okay, and then multiply by a minus 3. Okay, we get a 0 here. We get, let's see, 7, minus, let's see, 175. Oh, sorry, not minus 3. Again, I'm doing the same thing again. Will not make Khan Academy. That's okay. Khan Academy videos are kind of boring anyway, so gotta have some faults. Okay. All right, so multiply by minus 1. All right, so we get a 0 here, and then what do we get? We get a 3, and then we get 5 plus 2, so it's a minus 3, and we get a 0. Okay, so then finally, going to multiply the second row by 3 and add it to the third row. 4, 2, 0, 0, minus 1, minus 1, 0, 0, 0, 0, 0. Okay, so quickly, you can see that there are only two pivots. Okay, there's a pivot here, there's a pivot here, right? So there are two pivots. And so since n is 3 here, 3 is not 2. So therefore, A is not invertible. Okay, so there are quick ways to check whether things are invertible or not. You don't necessarily have to find the inverse. All I ask is whether it is or it isn't. Okay, to find the inverse takes more work. So just to answer the question of invertibility, you can use, one of these 8 statements up here. All right, now we had the notion of linear transformations. So let's look at linear transformations just for a moment. And so we have t from Rn into Rn, and this is the linear transformation. Okay, and so we know that we can represent t as A of x, and A is going to be the matrix by taking t on the unit vectors and putting them down the columns. Okay, so whenever we have a linear transformation, we could represent t by A times x. Okay. Now, suppose A is invertible. And consider S of x to be equal to A inverse times x. Okay, so since A is invertible, A inverse exists, and then I could consider the linear transformation S of x by just applying A inverse times the vector. And let's just try composing the two. So t on S of x, this is t on A inverse of x. Well, this is going to be equal to A times A inverse on x. And A times A inverse is the identity, so I just get x back again. And then similarly, if I take S of t of x, I also get x back again too, by a similar argument. All right, so what I'm saying is that t times s, or t composed with s, is the identity, and s composed with t is the identity too. So what that means is that s has to be the inverse of t. So what I've shown is that the inverse of t is just given by the matrix ax times x. So if A is invertible, I can write out the inverse quite nicely. Let's try to keep it a little bit neater here. Oops. We'll try to keep it a little bit neater by. Okay, so let's try this a little bit better. No, that looks a little bit better. Okay, great. So we can connect this up with linear transformations. It's not very difficult. I mean, it makes a lot of sense, I hope. All right, so I have a few extra questions. So these are additional questions. And these questions are here to sort of challenge our sort of thinking and our understanding of the material. All right, so let me state some of these. So first of all, explain why a squared is invertible if a is invertible. Okay, so you want to explain why the square is invertible if a is invertible. Okay, so there are several ways to do this. So first of all, suppose a is invertible. Okay. All right, so one way to do this is just to use our old method using the homogeneous system of equation. So we should consider a squared x equals 0, the homogeneous system. Okay, so what does this mean? That means that a times a of x is equal to 0. But what do we know? We know that a times something time is equal to 0. Well, a is invertible, so that means that ax has to be 0. So we know that ax has to be 0 since a is invertible, right? Remember, a times y equals 0 has only the trivial solution. So the thing that's inside has to be the 0 solution. Okay, now we just repeat it again. So we know a is invertible, so that means x has to be an invertible. Since a is invertible. Okay, so what was our conclusion? Our conclusion is we start with ax equals 0, we conclude x equals 0. So by the property earlier, we have to have that a squared is invertible. So a squared is invertible. Okay, so similarly, let's try a different problem. So this is a similar type of problem. So show if a times b is invertible, then b is invertible. Okay. Well, we can basically, I mean, we can sort of use the same type of argument, right? So remember that b is invertible if and only if bx equals 0 has x equals 0 as its only solution. Okay, so that's what we want to basically show, right? So consider bx equals 0. All right, now I want to show that I want to use the fact that a times b is invertible. Well, how do I get the a times b in there? Well, it's kind of obvious, right? You just multiply both sides by a. So that means that a times bx has to be equal to a times 0, which is the 0 vector. So now you use associativity, a times b times x is equal to the 0 vector. And now we know that a times b is invertible, So that means x equals 0. So x equals 0 since a times b is invertible. Okay, so this sort of follows the same line of reasoning as like the first problem. Okay, you just have to keep everything straight. So the logic has to be very clean, and you have to argue using those equivalencies. Okay. All right, so my final problem of this session is the following. So show if A has linearly independent columns, then A has linearly independent rows. Okay. All right, so let's kind of think about the equivalent statements. So A has linearly independent columns if and only if, so this is my if and only if statement, A is invertible. Okay. And I can write A has linearly independent rows. Well, if I transpose A, remember the rows become the columns and the columns become the rows. So, using a little bit of logic, that means that A transpose is invertible. Okay, so what we can do now is we can just use our little formula for the inverse of the transpose. Okay, so suppose A has linearly independent columns. So we know that A is invertible. And A inverse exists. And so we have that A transpose, the inverse, is going to be equal to A inverse transpose. That's our little formula for the inverse of the transpose. And since A inverse exists, A inverse transpose exists too. Okay, so this one exists too. We can form this. And so A transpose is invertible also. Okay, so A transpose is invertible, so A has linearly independent rows. So therefore, A has linearly independent rows. Okay, so that actually finishes everything off. All right, so remember, when you look at these type of problems, understand what your hypothesis is and understand what your conclusion is. Start with your hypothesis. So this is a hypothesis. And this is the conclusion. And then you have to argue logically from your hypothesis to your conclusion. Okay, so again, I thank you for your attention on this, and we'll see you in class next week.